Okay, so this is one thing, that this is not true. This is just a misconception about quantum mechanics, that it works only at the microscopic level. This is not true at all. Rather, quantum mechanics is not only is that it works for superconductors and magnets at the microscopic level. Rather, quantum mechanics is a paradigm to understand the cosmos. This is the modern paradigm to understand the cosmos. And you must be I think maybe not must, you may be familiar with the work by Stephen Hawking and other people who are trying to apply quantum mechanics to the black holes. And that's what is presently black hole. As you know, what can be bigger than a gravitational object as a black hole? It's quite important gravitational system, and people have tried to apply quantum mechanics to those things as an isolated phenomenon, not as, I would say, as part of quantum gravity. So this is to tell you that this is entirely wrong to say quantum mechanics is something which talks about atoms, electrons, and microscopic level. Then it is not true at other levels. This is a one misconception which I wanted to clear. If you have any questions and comments, please keep on writing them in the chat box. Now, another misconception which we have about quantum mechanics is, comments and questions, please put them in a chat box. Okay, the another thing is, there is another misconception that quantum mechanics can be, it is basically what we do is that we get quantum mechanics, okay, or quantum theory, I would say. For quantum mechanics it may be proved. The way we get it is that we start from, what I want to say is that, so there is the arrow is this way, so we say that, okay, you start from a classical system, and then you quantize it, then you get a quantum system. Okay, well, this is true. This is called the correspondence principle, which Bohr and other people talked about, and it is true for many classical systems. Like as any mechanical system you take, there is always a quantum version. You go from classical version to the quantum version. That is true, but this is not true for every case. I will just point out one important example. It is your favorite example is the electron. Electron, as you know, is a fermion, and fermions, if you just try to get a corresponding classical correspondence for a fermion, or even similarly for a spin phenomena, there is no classical correspondence. Okay, so this is just one example, that there may be quantum systems for which there is no classical analog. So it is not always possible that you start with classical mechanics and then you quantize and then you go to the quantum mechanics. What it tells us, for us, at least for the fermions, so the starting point is not classical mechanics, rather starting point has to be quantum mechanics. Then you, whenever classical correspondence exists, then you go back to the classical description. If it does not exist, then you have only quantum description available, like as we have for fermions and spinorial phenomena. Okay, so this is another misconception, because typically the flow goes this way. People take classical mechanics as because historically it was discovered first, it was developed first rather, and then we did quantization later on. Then they think maybe classical mechanics is more fundamental, and then we have to just add quantization on that, then we go to the quantum mechanics. So historically this was the route that was taken, but this is not the entire story. Okay, quantum mechanics, as of now, it stands as of now, it is much more fundamental than classical mechanics itself, and there are ways to explain some quantum phenomena right from just taking a classical correspondence, classical limit, what we call as. So that way quantum is I would say more fundamental. That's the approach we take. Third point which we have is now quantum mechanics as compared to our classical mechanics is we get very irritated by statistical nature. That's what happened to the Einstein also. We get very irritated with the statistical nature of quantum mechanics or quantum theory. Okay, because when it is a statistical nature, we think, okay, because it is statistical, because it is probabilistic, it is an approximate version. We will not be able to know the nature. We will not be able to calculate things accurately. We cannot have an accurate calculations. We cannot describe nature. All we can do, this is the common thing which you get to listen. The only thing which you get to know is probabilities. That's what you can calculate about the things. Okay, now let me give you an example. Magnetic moment of an electron. This is one of the important quantities, and let me tell you, it does not take just quantum mechanics, it takes quantum electrodynamics, which is full version of a quantum field theory, to calculate that magnetic moment. And this magnetic moment there is a small difference, few digits difference between, and that will be maybe on the 8th or 7th digit where the difference lies. It was the precision which theoretical physicists, the calculation was done to a very the agreement between experiment and the theory is so accurate that people, it was really stunning for everybody. So the fact that anybody tells you, or you think that quantum mechanics is statistical and therefore we do not calculate exact things, that is wrong. We will come to it. Everything will be explained. I'm just telling you what are the common misconceptions. And I will just give another example. If we were not able to calculate exact things about nature, about atoms, molecules, everything, hydrogen atom, everything, so how do we then calculate the energy levels? How do we know the energies of hydrogen atom, of the helium atom? How do we know the band structure? How do we know that what is the Fermi energy? What is the of a metal? How do we calculate those band gaps for semiconductors? Okay, how do we know the what is the superconducting gap of a superconductor? So how do we know all those things? If we were not able to, if the probability is the only thing we calculate, then we should have calculated the probability that the energy of hydrogen atom with being in S level, and the energy will be this much. That is the probability, which we will not know the exact value, but we know the exact value. We know the what is the energy of an electron in S level, P, D, whatever it is. Okay, we know all those exact numbers. In fact, quantum mechanics has been one of the most exact theories that has ever been developed in human history. Okay, so that is one other thing. We will, I mean, definitely, maybe when I am saying it, it may not be fully clear to you, but I am just trying to pinpoint that the way we have to approach, the way, how do we basically clear our doubts, and how many doubts are there, and these are some of the common, which we cannot, without clearing these doubts, we cannot go ahead. So that's what the thing is. Another thing is which people talk about is this was told to me also when I was a master's student, that you cannot know the trajectory of an electron, you cannot know the trajectory of a quantum particle. Why so? Why is it that we cannot know the trajectory of a particle? Because of the uncertainty principle. Okay, first of all, uncertainty principle, the way it has been told to you in terms of delta x and delta px, that they are not talking about the trajectory. They are not talking about what happens in the real space. They are making a statement, something about phase space of the quantum system, not about the real space. So in that sense, what is happening between delta p and its conjugate variable is not immediately available, is not applicable to space, because space means between space, that the relation between motion is the relation between position and time, not between a position and it is another thing. Momentum arises as out of dynamics, so it has nothing immediately to say about the trajectory of the particle. And let me tell you, there is a full Richard Feynman, which you all are familiar with. He developed one of those approaches, and though one of the approaches to quantum mechanics, in which you always talk about the trajectories of the particle. The Richard Feynman's approach to quantum mechanics is based on the trajectories, real-time, real space-time trajectories of the particles. If it was not possible, how did we get those path intervals? They are called path intervals. And that is one of the important developments which we have from Richard Feynman. So it's entirely wrong to say that we cannot. And another simple example is when you do double slit experiment, you talk about that electron goes from one point to the another point. It goes through one slit, then it goes. When we actually did the double slit experiment, the electrons are going, they are following a path. That's why they are going from light electron beam source, or they are going from light source if they are photons, then or they are reaching that double slit screen. If they weren't, so they are going through that, and then sometimes it is I mean, there are some experiments where you closely look at a one photon or a one electron. They are called weak measurements. Okay, you are closely monitoring it where it is going, so you get it in some sense of space-time coordinates. Because even if we apply Heisenberg's uncertainty principle, that is not applicable between position and time. And trajectory is about position and time. It's position as a function of time. That's what you want to determine. And position you can entirely determine. So this is entirely wrong to say that you cannot determine a trajectory of a particle. That's wrong. Then the fourth point from a learning point of view is people think quantum mechanics is mathematically more challenging than classical mechanics. This is not true once again. Quantum mechanics is mathematically very, very simple. All it needs is, it does not need any much of calculus. It needs your course in linear algebra. Mathematically, the background which you need for quantum mechanics is just linear algebra, and I mean some part of linear algebra, which we will cover anyways. While as if you look at classical mechanics, it is based on many things. One is called calculus of variation, and calculus of variation is such a advanced and sophisticated subject that many of you would not, when you take a book on calculus of variation, start reading it, and you will see the kind of subject it is. It does not talk about functions. It does not talk about it. It talks about something called a functional. Functional is an object which takes functions as input and spits out the functions as output. It's a highly sophisticated mathematical object. What we deal with the calculus of variations, it is a part of, we can call it is a part of functional analysis. And functional analysis is a hell lot of difference between vector linear algebra is a lot more simpler to deal with than functional analysis or calculus of variations. Okay, so that is the background, and that is not all. It also talks about phase spaces, and phase spaces, if you look at from a geometry point of view, which becomes important in classical mechanics, the geometry of the phase space, which is symplectic geometry. So that is so advanced as compared to the quantum mechanics, where you never talk about so much about geometry. Geometry does not come into picture as such. You would never see calculating areas and distances about in quantum mechanics. It becomes important. It's not that it does not important, but it does not become important like that. Okay, so that way this is mathematically very simpler as compared to classical mechanics. However, okay, what in our even my own language, there's a but over there. So the but is that we cannot the classical, what is the challenge with quantum mechanics is it has a radically new conceptual structure which was not there neither in Lagrangian mechanics, neither in Hamiltonian mechanics. What we will explore some part of that radical nature. What is it that which makes quantum mechanics radically different from classical mechanics, and because of that we are having problems with it. Otherwise problems are not mathematical, even if, I mean, as a subject it is not. Maybe our teachers are not teaching us rightly, but if you take the level, if you compare linear algebra with functional analysis or vectors, this calculus of variation, there is a lot of difference. There are a lot of sophisticated stuff happens on calculus of variation. So so these are some of the misconceptions which we have, and because of that we get into different kinds of doubts. Okay, so let me take, if there are any questions about these things, I will take them immediately, and meanwhile if not, then I will move on, then we can go to other stuff. Okay, anyways, so they are being dealt with. So let me in that case I will go ahead and let's talk about some more stuff. Okay, so now let's take this stuff here and let's come to another thing. Okay, now one of the basic things, now let's turn to, now we are starting actually our first, let me call it chapter or a unit of quantum mechanics course, which is the mathematical preliminaries. Let's first of all build our mathematical background so that we can become comfortable in quantum mechanics itself. And as you know, you see, when you take any textbook on quantum mechanics and you look at the mathematical formalism, it starts with vector spaces. Now we were familiar with vectors, vector algebra, vector analysis. Now we think, what is this vector space? Okay, and why does it become important in quantum mechanics anyways? Okay, so today what we are going to do is we are going to, I will call it debunk and deconstruct all the ideas, all the misconceptions, or the way we would have done it. I want to show to you that you are all familiar already with vector spaces. There is nothing scary about vector spaces, and in fact you have, from the very early days, school days, higher secondary days, you have been living with vector spaces, and it's a very important concept. It's a very special concept. However, it is not that it is special to quantum mechanics only. I mean, if you don't know vector spaces, you will not learn quantum mechanics at all. As I suggested earlier, as I mentioned, there is another approach by Richard Feynman which does not talk about vector spaces at all. So you can take a path integral approach where you don't have to talk about vector spaces. However, I would say quantum mechanics has done a great job in making vector spaces very important, because vector spaces are anyways very important. You don't, not only in quantum mechanics, they are not special to quantum mechanics only. They come in many other places. Therefore, let us get head on onto this concept and try to understand what it is. And as I said earlier, I want to today show you, that will be the last part of our lecture, technical part, to show you that you are already familiar with vector spaces. We just want to revisit those early areas. Okay, now let me remind you, and this is something, one of the things which will happen in this course. You will be presented the ideas and methods and quantum mechanics in a very different way, the way you would have, you will not find it if you take any quantum mechanics book. Typically they don't present it this way. So one of the things which is very unconventional in our course is we will present vector spaces to you in a way that maybe you would not have even thought about. Okay, let me basically get started this way, that let's talk about, before we come to the quantum mechanics, vector spaces itself, let's remind ourselves about the interference of the waves. Okay, uh, let's go to the very simple things, very basic things which we already understand. Okay, and let us to just give you a heads up, we will see interference has something to do with the vector spaces or vice versa. Okay, and what happens in interference, as we know that we have two waves, they are coming together, they pass on through two slits, let's say, then there is a superposition which happens between two waves. Depending on their phase differences, they can interfere constructively or destructively, and that is the interference pattern which we get on the screen. Okay, that's what happens. So interference, for interference, what is important is that the waves satisfy this, they have this property of superposition, they come together and then they superimpose each other, and then they lead to the result, which is the wave pattern over there on the screen. Okay, the interference pattern which we call as, that's what happens in interference. Okay, now we know, let me write the simplest let me write the wave equation. Any wave equation has this structure, that it is basically or if I like it three dimensional, it has the delta square of some function psi of x, v, y, and z, and maybe of t also, and then we have some constant, let me call it kappa, and then we have d2 psi of dt2. This is more or less the structure of a wave equation looks like, that you have second order derivatives on the space side, they are related by some constant with the second order derivatives on the time side, and this kappa is related to the speed, the velocity of those waves. Okay, now what is important about this equation, wave equation, is that it is second order, its degree is 1, but its order is 2. Okay, so but degree is 1. When its degree is 1, it means it's a linear differential equation. It's a partial differential equation, but it's linear. Okay, so if I want to, I maybe what I would like to do is that I would want to make a simpler version of this thing. Let us go to a simpler version, which is which is simple harmonic oscillator itself. That may be more easy to deal with. So we have this equation, very simple, interesting equation of omega square y is equal to 0. Okay, now this equation is very important for us. Let's try to see, and let's ask ourselves, what has this equation to teach us about vector spaces? I am telling you everything. We are going to learn our vector spaces from this simple, beautiful equation, which we learned back in school days, back in high secondary. Okay, so first of all, as we remember, as we know from when we look at this equation, differential equation, we know that it is it's once again a linear differential equation. When it is linear differential equation, means it also has, linear differential equations has this property that its solution satisfy something called a linear superposition. This is the property of linear differential equations. Okay, that's why we many times we call our principle superposition principle, we call it principle of linear superposition. Okay, because superposition typically is valid if you have a linear differential equation. So now let my it has two solutions, two independent solutions. Let me write the form of them. Say a sine omega t is one of them. Then I have y2, which is b cos omega t. Okay, so this is another solution. Fine. These two solutions, they are two different solutions. Okay, this one and this one, there is no way we can convert one to the another. Okay, now but what we can surely do is we can combine them together. We can write y1 plus y2. Okay, let me multiply them with some numbers, real numbers, c1 and c2. Okay, and this is basically the ability, this property, mathematical property of these solutions as a as a solution to this differential equation, which follows from the linearity of the differential equation, is a wonderful property. And it is this property of, same is true for the wave equation also, because it's also linear differential equation. It allows the superposition to happen. So superpositions and interference phenomena happen from a mathematical point of view because they are solutions, waves and oscillations, or solutions of linear differential equations. Okay, so and this is the mathematical statement of a linear superposition, that given solution is given, in fact they should be linearly independent. We will come back to linear independence later on, but they should be different solutions. Okay, then you combine those two solutions because it is at order 2, that's why it has two different solutions. So you have these two different solutions, then you combine them together, you will get another solution. If you take now this y, which will be a sine omega t plus b cos omega t, you will see it will also satisfy the differential equation. Okay, so there are some undetermined constants a and b. We will have to take care of them if we apply some boundary conditions. But the fact that this still remains a solution, it still remains part of the solution. So let us formalize it mathematically. So we will say we have some space called a solution space. Okay, in solution space we have two kind of guys. Solution space means it's just a set in which solutions of this differential equation lie. So there are two special guys, y1 and y2. Okay, then there are, I will call them superpositions. Okay, these two, y1 and y2, these are, I will call them basis solutions. Okay, why I am calling them basis solution is because any other solution can be basically either decomposed into these two, or in a reverse manner you can compose any superposition out of these two basis solutions. Okay, and this property is called the linear superposition property of these solutions. Now what has this thing to do with the vector space? I will say everything. The property, that equation which you are looking at here, this particular equation over here, so this has everything to do with the vector space. In fact, this is, I would say, this is the definition of a vector space. We are coming towards that. We will make it more mathematical. But what is it now? Let us take a breath, take a breath, and look at this equation again. I am telling you this is the definition of vector space. Vector space is any space, okay, in which what happens is that what you can do is that you basically can take a linear superposition. Taking a linear superposition is one of the most, this is the defining property of a vector space. If you now take a mathematics textbook, you look at a vector space definition, you will not see it. It will not come clear to you that it has something to do with the linear. We are taking a reverse engineering approach. We are basically taking our path starting from superpositions and going back to vector spaces. The superpositions are possible because the solution space is a linear vector space, is actually a linear space. So but what is, so first of all, I think this part is clear, that we have a linear superposition. Now let us go back and make it ourselves clear, how is it a vector space? Okay, now before I do that, I just want to remind you one more thing. I just want to remind you of your early classes when we studied vector algebra. So when we studied vector algebra many years ago, so what we studied there is a very interesting property which I used to love. It's called resolution. It's called the resolution of vectors. Vector resolution we call it. Okay, let's say I have a R as any vector. I can write it as x ex plus y ey. Now look at both these equations parallelly. Look at simultaneously at both these equations. There is a striking similarity between what I have written for solutions of a harmonic oscillator, differential equation for that, and what we have studied in our vector algebra class. Okay, so both these properties are same mathematically. There is no difference. X is a real number. Ex and ey are basically basis vectors, and y and y1 and y2 are basis functions here. Okay, so I'm just trying to connect the dots for you to tell you that vector spaces are something which you already know. There is nothing special about it from a quantum mechanics point of view. Now let's go and ask ourselves again, what is a vector space anyway? What is the mathematical definition of a vector space? Okay, and then we will identify that we have all those things here. So therefore our definition, my definition of a vector space is any space, a set with some properties. That's what a space is in maths. it is a space where you can take a linear superposition. And this definition, if you look out from books, you will not find it. Show me the book where you find it. I'm not saying that I have designed it, but I'm saying they don't highlight these properties. They just give you some axioms, and then you are left with those axioms. Okay, now we will start from these properties and go back to these axioms. Let us come to the now vector space definition. And by the way, I want to make a clear-cut distinction between between these two spaces. There, the space which we are looking here, the linear superposition here, this is also some sort of a linear superposition. And what we have seen in over here in the for the differential equation, solutions of the differential equation. What is the difference? The difference is that in vector algebra, we always know how do we calculate the magnitude of that vector. We also know the distances between two vectors. So there's a concept of the distance already there. Fine. However, if you go to this one and I ask you the question, tell me how different or what is the distance between one solution, one oscillatory solution to the another oscillatory solution. Or if I ask you a question, how apart are they from one another? Is there a notion of distance defined on the solution space? You will see there is no, we cannot just define it. It is not defined anywhere over there. The linear superposition does not need that. So linear superposition does not depend whether we know whether a wave knows, whether a solution knows, one oscillation knows how far, what is the distance of one. Even it is not even applicable. You cannot talk about these things in this sense, the way we talk about vector algebra. Okay. Therefore, the actual name of vector spaces is not actually vector space. Vector comes because there are vectors also, actual vectors. Actual name is linear space. Okay, that is what we initially need. So linear space is the actual name, but we also call them vectors for the reason because vector algebra, which we know, is also some sort of a linear space. Okay, what is this linear space? And let me give you now the mathematical definition of it. Earlier I said that from a physics point of view, vector space is any place, a linear space is any place where it is possible to take superpositions of this sort, like as we have here. Okay, these are the superpositions, which basically means you will have some basic vectors or basic in solution space we have functions, we do not have vectors, but you should have those functions. You can combine them by multiplying them with the real numbers, and you can come up with the new solutions, many of them. Okay, you can always have that solution is coming up. Understand? However, once again, if you look at, if I later on, it becomes an important property of vector space or linear space is it is dimension. But if you look at the dimension of both these spaces which I have written, dimension is still 2, because dimension has something to do with how many linearly independent solutions we have, which are anyways 2 here. And similarly, I have basically taken only 2 here also. Okay, so in this case also I have just 2 vectors of them, so it's also 2-dimensional. It's a plane, a real plane. So that's the concept of the dimension here. And now let's come to the definition. Final thing is the definition. So linear space is a space. Space means it's a set with some properties, with some addition law or something. Okay, what it should satisfy is it should have first of all set of, it's a let's say set of, let's call them vectors, functions, whatever it is. It's a set. It's just a set with addition defined, some sort of addition defined on that, which we have on solution space. Because where is that addition coming from? Superposition. Superposition tells us that you can combine these 2 solutions, 2 oscillations can be combined to give us another oscillation. Okay, that is the addition over there. Similarly, in vectors also we have addition. So addition property is there. Fine, that's why we have superposition. Okay, we have addition. Then what should be the property of the addition? Some simple properties, that it should be commutative. Let me talk the solution space. It is commutative. Okay, for waves it does not matter which wave came first, this wave or that wave, whichever wave they come, interference will happen. There will be a superposition and you will get the result. It does not depend, the order of the waves does not depend. So similarly, if you want to make the associativity also true, which is possible, maybe we can make a new solution which will be combination of something. Let's call that y3. Okay, but this y3 is not a basis vector. It is, we have got it some combination from y1 and y2. And if we have that, then what we do is that we have y1 and y2 again. You can see because of this property, we will do vector addition. So we'll take these 2 together. It is easy to see that what we will get is we will have y3 separately and then y1 plus y2. Okay, so this follows because the way interference will happen, if we take our definition, if we take a physical point of view, it will happen because two waves will superpose first, then they will superpose with another oscillation, then we will get the result. Same thing will happen, we will have first two in another order, we will have superposition happening, and then we will get the another same result we will get. So the superposition does not depend on the order of the oscillations, the way they are coming. it just what is important is that those oscillations are coming together, waves are coming together to make the interference pattern happen. So that is the reason linear superpositions do not depend on the order. So associativity property is there. Similarly, you have some additive identity, which means you should have some solution y plus 0, which you should give you the same thing. Okay, then we have some sort of an inverse also, minus y. So how do we get these things? This is a trivial solution to the differential equation. This is always a solution, so it's already there in the solution space. It is always there. And how do we get this one? We get it by defining it by multiplying it minus 1, which is a real number. We take minus 1 and multiply it with any solution, and we have this one. So these things and all of it satisfies that we should have what we in math is this is a language. You should not get bothered or intimidated by this language. You should try to understand what does it mean for me as a physics guy. Closure means if two waves are coming, is that what I get out of the superposition, is that also a wave? If two oscillations are coming together, is that also an oscillation? Yes, we know in physics, we know oscillations come together to form oscillation. It never happens oscillations come together, they give some different thing. It never happens like that. So linear superposition is a property in which closure is already satisfied, which means linear superposition tells us that whenever you have oscillations, whenever you have a solution space, you can always combine them together to get the oscillations. So linear superposition satisfies that. In fact, the statement of the linear superposition as a property of waves and oscillations is that whenever you combine oscillations together, you will get oscillation. Whenever you get another solution to the differential equation mathematically, similarly you get waves together, you will get waves. That is what in mathematics we call it closure, which means given two vectors, we should get the third vector. That third vector should belong to the same space. Okay, that is what closure means. So you should have this property. Then as you see already, we have other thing also. If we go back to our equation, so this linear superposition is not possible if we have just y1 and y2. If we have just y1 and y2, we will get another third vector of another solution to the differential equation. but that's it, we will stop there. If c1 is equal to 1, c2 is equal to 1, then we stop, we will get only 3 solutions. However, if we allow that we take these c1 and c2 from the real number field, we have the real numbers, we take whatever real numbers we need, then we have what it allows for us, we have so many solutions available as oscillations. Okay, so linear superposition depends on two things, that you have these basis solutions, which for second order differential equation will be 2 of them. Then you should also have the numbers, because with those numbers you can combine them together and then you get a linear superposition. Understand? So linear space and the solution, as I said, it comes with the linear space has 2 components, has 2 ingredients. One is the basis vectors, basis functions, and then also the numbers. Numbers we call them scalars, and the y1 and y2, they are basically solutions of the differential equation. However, we call them vectors because now this is the definition. Because they belong to something called a vector space. Vector space is a set which satisfies these properties. And for the scalars, the properties are very similar, very simple, which you expect anyways. That if you have 2 scalars, you multiply any scalar with y, what should happen is that you should get something of that sort, that it will get multiplied first and that another will get multiplied. Something like that, the very, very simple properties of the scalar multiplication, okay, which we are already familiar. Similarly, you should have, if you have c1 plus c2, you multiply it with one solution, you should get c1 y plus c2y. Similarly, if you have c1, you multiply it with, you take it to 2 c, you take it to multiply it with 2 guys, and you should get cy1 plus cy2. And as you know, this all of it is satisfied by linear superposition. So these are various axioms, and then there is some maybe some identity in the sense multiplicative identity. There should be some unit number which you can take c is equal to 1 and then you multiply it with this. So all those things are satisfied by linear superposition. Therefore linear superposition is, whenever linear superposition is true, and for all those functions for which it is true, that becomes a linear space. We call it linear space. Why do not we actually, the actual mathematical name is the linear space. What is a vector space then? What is the difference between linear space and a vector space? In a vector space you always have scalar product defined, while as in the linear space you do not need. For linear superposition you do not need the concept of distance, you don't need the concept of the dot product, you don't need any of that. You don't need to know the magnitude of your vector. Okay, so linear space is a set of solution. It can be anything. Let's say it can be a solution to a differential equation, to a wave equation. It can be any function, it can be any vector, whatever it is, whatever set it is, it has to satisfy this thing that you can take some basis solutions from that set, and you can get all other members of that set by doing the linear superposition. So linear superposition is the central piece of vector space, linear space, and that is why it is in quantum mechanics. Because in quantum mechanics, one of the important reasons why is it there, in quantum mechanics, we do not have a usual linear superposition. We have something called a quantum superposition. Quantum superposition is the central ingredient, central aspect of quantum mechanics, and without that, I don't know, it's a very, very important aspect of without that I don't think we will lose lot of its structure. So therefore that is why, that is the connection. Why is it that one may ask, why do we bring these linear spaces to quantum mechanics? Because in quantum mechanics we have to explain quantum superposition. The way we explain quantum superposition is in terms of linear spaces. How else will you explain it? Okay, so I think I will stop there. This was to just to give you a kind of a glimpse of just to give you a definition and examples of what a linear space is. And this linear space is something which you are already familiar with. You know, solutions of differential equations, they are linear spaces. And I will give you more examples as we go along. But these, I just want you to take some of the examples from what you would have studied earlier. And this, whatever we just studied, we will apply it later on to quantum mechanics. The same thing, we will explain everything over there in quantum mechanics. To begin with, we do not need anything more than that. Now, the statement which I make about quantum mechanics right here is, is this statement that in quantum mechanics, like as in classical mechanics, first of all, let me talk a little bit about classical mechanics. First of all, if we are in a Newtonian regime, okay, then our space, we always have state space. The state space is actually Euclidean space in which the motion is happening. Okay, so that's what it is. If we are in Lagrangian dynamics, so then in that case we also have a state space which we call as configuration space. Okay, so which basically means various combinations of q and velocity. And if we are in Hamiltonian dynamics, we are in classical one, then we deal with the state space becomes the phase space. Phase space is a space in which you have momenta and coordinates, generalized momenta and generalized coordinates as your coordinates of that space. Now in quantum mechanics, this is one of the big differences. You will notice some of the differences. The big difference is that here you are in quantum mechanics, when we come to the quantum mechanics, what is our state space? Our state space, state space of quantum mechanical system is first of all, before we get to the other stuff, first of all, it is a linear space. And what is a linear space? Linear space is a space where you have linear superpositions. As simple as that. This is the simplest definition you can ever come across about vector spaces. And it connects the physical intuition. Why is it that I mean, why the heck? I mean, why should we use these things there? I mean, we should have a reason, fine. If somebody tells me and says, I want to use this path integrals, he should give me a motivation why I'm using it. It should not like that. It is somebody, I mean, it just came to his mind and then he says, okay, I'll go ahead with it. Okay, I should have an explanation. This is physics, this is science. I should have, they owe me an explanation if they are telling me these things. Okay, so that is what the thing is. And one important aspect of it is that this is to be very highlighted, that unlike classical mechanics, Okay, earlier I made a comment that quantum mechanics is much simpler than quantum mechanics, which you may not agree with me. It will take you some time to agree with that because you may not be so comfortable with quantum. But one of the important thing, another important things is that quantum mechanics is linear. This to me, I call it miracle. I call it miracle that the world around us is non-linear, highly non-linear. Then the most exact theory of that world around us, you tell me that that's a linear theory and you will be able to explain everything around us. Yeah, that exactly is the case. That quantum mechanics is a linear theory. What do I mean by that? The linear theory, it is a linear theory. I mean the structures which we use in it, the spaces, transformation, everything is linear. We don't, Schrodinger equation is linear. Heisenberg's equation of motion is linear. We use linear spaces over there. We use linear transformation. So linear theory is a theory in which we use just linear structure. Okay, and what is the linear structure? Linear structure is that, because in quantum mechanics we have two things. One is the linear space, so we have linear spaces, we have linear transformers. Okay, these are the two things which make the state space whole thing, operators, observables, everything in quantum mechanics. I'm telling you, this is a miracle. I mean, you just think about it. The world around, take a simple example of the harmonic oscillator, the pendulum over there. Okay, and we know it's non-linear. It's not linear, is just an approximation to that. Now the same harmonic oscillator, which is at a level of let's say I take a quantum harmonic oscillator, which once again is doing vibrations, but I have a linear theory for that. I'm able to explain what is happening in solids. In solids there are vibrations, we call them phonons, quantum version of that, and with that I explain a lot of stuff, but based on this linear theory. Okay, it is definitely a miracle. So let me summarize some parts of it. I think I motivated you that linear spaces are something which you are already familiar with. This is not something new. You don't have to learn something new to understand quantum mechanics. You already know it. Euclidean space, which you have been always studying, R3 or U3, E3, what we call the usual space which we live in. So that is one of the best examples of the vector of the linear space. You just take all the axioms of a linear vector space and just apply it to your vector algebra. Vector algebra. Okay, now the answer. Why was that vector algebra working? What is that vector algebra? That whole vector algebra which you are doing is, those are the axioms of a linear space. Those are the axioms. You just go back to your vector algebra, check out. You will see in vector algebra we studied a plus b is equal to b plus a, which is the commutative property. Then there is an associativity property. Then there is a unit vector. Then there is a inverse vector. So what are they? What are they? What vector algebra? Where is it coming from? Vector algebra. Vector algebra is coming from here. Yeah, I just wrote somewhere. I just wrote some axioms. So all those axioms here. Yeah, I was saying that it should have. What is the definition of a vector space? It should have a vector. It should have addition. Any addition defined. It should have commutativity. It should have associativity. It should have a additive identity. It should have an inverse. That is exactly what vector algebra has. So vector algebra is already a linear space, and the reason you are able to do vector algebra is because it is a linear space. Then it has other properties also. You remember scalar multiplication, which you would have studied. So you have studied first example of a vector space and a linear space in your 11th standard. It is just that person who was teaching you, he did not tell you that we are talking about linear spaces. So the linear spaces which we need in quantum mechanics, we have studied them in 11th standard. That's why maths is simple. The maths which we need here is very simple, and in this course we will make it even more simpler. Understand? So I think this is where you please you have to remember it. That's how it works. That same. Okay, you may say, some smart guy among you will tell me, okay, so you are telling me that the vector algebra which I learned in 11th standard, same thing is applying in quantum mechanics? The answer is yes. Obviously yes, a big yes. Yes, that vector algebra which you studied in your 11th standard, we are going to use the same vector algebra, nothing new. What is new? These people, these English people, that's how they say it. They will bring something called a bracket notation, and we are lost. Buddy, there is something going on over here. I am telling you, dear friends, nothing is going on over here. Just decode it. You will see all what is new. Like as you take any book on Sakurai. Why is Sakurai looking so difficult to you? Because it is in bracket notation. And now you think, oh God, I don't know what is this bracket notation. Bracket notation is nothing new. There is nothing new. There is no math. There is no physics in bracket notation. It is just a symbolism. It is just a notation. Like as in tensors, we use Einstein summation. Here also we use the summation. I mean, it becomes life becomes easy. I mean, ultimately, maths people or physicists are humans. They want to make their life easy. Okay, so that is what it is. I think this is the most important message which I wanted to share with you all in this lecture, that in quantum mechanics the state space is a linear space, and that's what we need. And I gave you the definition. The physical definition of a linear space is a space where you have linear superposition being satisfied, and once you have the linear superposition being satisfied, you have all the axioms of vector space being followed. Okay, then we will continue this technical part inshallah in next lecture. I just today wanted to warm up you with the concepts, with the different things, so that we can make a connection. We will get started something. I think our starting point today was a linear space, which I try to motivate you that it's a very, very familiar concept. There is nothing special about it. We always have knew it. Okay, with that I will stop here, and we will go back to the questions and other things before we close.